Dot product part 3. We're going to talk about vector projections in this section. And first of all, a definition. Projection of u onto v is equal to u dot v over magnitude of v squared times vector v. I'll derive this for you in a fourth video. We'll put the derivation there, and that's optional, I guess. So what this represents is, suppose we have vector u, could be in the first quadrant, could be anywhere, and we have vector v going off in this direction. U's here, v's here. You can make a right triangle. Projection of u onto v is just simply this vector, which is the adjacent side of that right triangle. We're projecting u onto v. It's kind of like a shadow casting down. And then we have what we call w perpendicular is u minus the projection. That's actually this perpendicular component over here. So we've actually resolved u into two components, a component parallel to v, a component perpendicular to v. And if you take this vector and move it over here, you'll see u is equal to vector sum of this plus this. We'll talk about that in a minute. First, an example, computational example. Keep in mind that this right here is just a number. It's a scalar. And we're going to plug u and v into this, compute this, just get a number, and then multiply it by v. It's not as complicated as it looks. Let's suppose u is 1, 2, 0, v is 2, 1, 1. Projection of u onto v. This is a good way to work it out. If you try to do too much at once, you'll get the wrong answer. Write the formula. Replace u with the vector equivalent. Replace v with the vector equivalent. Replace v with a vector. Replace v with a vector. Get all the vectors in place. Now do the operations. This dot product is 1 times 2 plus 2 times 1 plus 0 times 1. This magnitude is square root of 2 squared plus 1 squared plus 1 squared. But we have a square here. This square is this square right here. And then we copy the vector down. Now we're going to figure out the scalar coefficient. 2 plus 2 is 4, plus 0 is 4. 2 squared is 4, plus 1 and 1 is 6. The square and the square root cancels each other out, so you just have 6 times 2, 1, 1. 4/6, of course, is 2/3. You can distribute, and you end up with 4/3, 2/3, 2/3. Now, w perpendicular is just a simple vector subtraction. Again, write the formula. U is equal to 1, 2, 0. Projection is what we got for an answer. And subtract. 1 minus 4/3 is negative 1/3. 2 minus 2/3 is 4/3. 0 minus 2/3 is negative 2/3. So I box that in. There's our two answers. Now let's check. Very simple check is good at reinforcing what the simple geometry is going on here. There's two checks. First of all, we're going to add these two vectors together. Projection of u onto v plus w perpendicular is equal, our vector projection is 4/3, 2/3, 2/3, plus, let me come down below here, I ran out of space, negative 1/3, 4/3, negative 2/3. And that's equal to 4/3 minus 1/3 is 1. 2/3 and 4/3 is 6/3, which is 2. And 2/3 and minus 2/3 is 0. Okay, and guess what? Where does that vector come from? That is vector u right here. Okay, so that part checks. Vector sum of that and that is vector u. That's exactly what we're doing. Second part of the check. Projection of u onto v, dotted on w perpendicular. We're going to dot these vectors together. 4/3, 2/3, 2/3, dotted on negative 1/3, 4/3, negative 2/3. Then we end up with 4/3 times negative 1/3 is negative 4/9. 2/3 times 4/3 is 8/9. 2/3 times negative 2/3 is negative 4/9. And guess what? We get 0. And 0 means orthogonal. Okay, now let's have a look at what that means. Geometrically, we saw that it was perpendicular. That, by the way, is a check. You should get 0 there. You may recall that cosine theta is u dot v over magnitude u, magnitude v. And if this is equal to 0, then it turns out u and v are orthogonal. And I just threw that out there as a definition related to the dot product. Well, what precisely does this mean? Assuming u and v are not the 0 vector, we'll assume then that the dot product is 0. When is cosine theta equal to 0? Theta is equal to 90 degrees. So orthogonal and 90 degrees mean the same thing if we have non-zero vectors. We have orthogonal means perpendicular. Okay, it's the same thing. Okay, of course, if we have one of these is a 0 vector, we wouldn't use the geometric definition of perpendicular. A point is not perpendicular to a vector, so that's worth defining. That's a simple way to check. It's good exercise. A lot of these basic vector concepts are not self-evident to most people. You have to work them out with a pencil and paper in order to solidify these concepts in your brain. So, okay, that's all for dot product part 3. So I did say there'd be a part 4. We'll derive the projection formula shortly.